In this video, we're going to solve this differential equation, dy dt plus 0.5y equals 0, by separation of variables. And here in this case, we'll go ahead and solve for y in the end. Okay, so that's what we want to do, solve the differential equation by separation of variables and then solve for y. This will illustrate some use of some algebra that you learned at one point. And in this exercise, what we'd like to do is illustrate why you did that algebra. So you'll see that as the problem unfolds here, our solution. So the first thing we want to do, let's move the 0.5y to the other side. So we have negative 0.5y over here equals dy dt. We multiply both sides by dt, and at the same time, let's divide by y. So we have dy over y equals negative 0.5 dt. So at this point, we've separated the variables. Now we integrate both sides. So on the left side, we have the integral of dy over y equals integral of negative 0.5 dt. The integral of dy over y is the natural logarithm of the absolute value of y. And over here, this integral, we could move the negative 0.5 outside and we'd have just the integral of dt, which is, of course, just t. So we have negative 0.5 t. And I forgot my constant on this side. There will be a plus, and let's put c2 over here. And let's get the constant back in over here. So this would actually be natural log absolute value of y plus a constant that we'll call c1. So ln absolute value y plus c1. And we can now subtract c1 from both sides like we did before. And so when we do that, we'll get natural log absolute value of y equals negative 0.5 t plus c3, where c3 is c2 minus c1. Now, at this point, what we want to do is go ahead and solve for y. So we need to get rid of the natural logarithm. And so to do that, what we'll do is we'll take e to the ln y on the left and e to the right-hand side on the right. So in other words, I call that e-ing both sides. There's no real technical term for that, but we have e ln of y, or absolute value y, equals e to the negative 0.5 t plus c3. Now the constant is now part of the exponent on our exponential here. So what happens now? Well, let's come up here. The left side, the whole point of taking e to the natural log of y, when we have e to the ln of something, so in other words, e to the ln u just equals u, because natural log and e are inverse functions of each other. So on the left side, we get absolute value of y equals, and over here, what we can do is this, whenever we have an exponent or an exponential and the exponent is a sum, that's equivalent to the same base with the two parts of the exponent but multiplied. So e to the c3. You're used to using this in the other direction. You've seen something like this. This is like an x to the a, x to the b, and the result of that is x to the a plus b, which is where we came from down here. Sorry, let me move that down a little. Okay, so again, this is like x to the a, x to the b, and that's equal to x to the a plus b, except we're going in the opposite direction. Rather than putting these together, we want to take this guy and take it apart into these two things. Now, e is just a constant. It's about 2.7, so constant to a constant power is then in turn another constant. So we'll put that out in front and call it c4. So we have c4 e to the minus 0.5 t, and on this side, absolute value of y. Now, if I was to tell you, say, for instance, as the absolute value of x equaled 5, then that would mean that x is either 5 or negative 5. So x would be plus or minus 5. And same thing here. When we say the absolute value of y is c4 e to the minus 0.5t, then that means y itself is plus or minus c4 e to the minus 0.5t. And what we can do is, and this seems a little bogus, but we can actually absorb this plus or minus into the c4. We don't know which one it's going to be, but either way it turns out, this is some other constant I'll call c5 e to the minus 0.5t. Now what this really shows us is why, when we've been solving things like this before, let's go back to our original differential equation. It was dy dt plus 0.5y equals 0. When we move the 0.5 to the other side and have dy dt equals negative 0.5y, what we're saying is we're looking for a function y whose derivative is negative 0.05 times the function itself. And we did this sort of thing before by guessing and checking. We said, well, y needs to look like e to the minus 0.5t, and in fact we discovered that there could be any constant out here, because when we then go ahead and do the derivative, okay, so y prime would equal e to the minus 0.5t. We still have our c out in front, but we need to multiply by the derivative of this by the chain rule, which is negative 0.5. So what we end up with is that y prime is negative 0.5 c e to the minus 0.5t. You can see this is our original y over here. So what we have is that y prime equals negative 0.5y. And that's what our differential equation was here when we moved that over to the right side. So we knew that before by our previous discussions, but this shows why the constant ends up being multiplied. Initially it is a plus c when you first integrate here, but it's because of these properties of exponents that it ends up being a multiplication in the end.